Welcome to the lecture series on numerical methods, a finite difference approach. In this method, last class we have discussed this Taylor series expansion and how we can just obtain this finite difference formulation using Taylor series expansion. And in this lecture, we will just discuss about this order of approximation, then the polynomial fitting, and one-sided approximation means if suppose a first order differential equation we are just solving, how we can just extend it to like more than 2 points. So that we will just consider in this presentation. So if you will just go for the overview of this order of approximation, especially in the last lecture I have just discussed that if we are just expanding any Taylor series, so this Taylor series can be written in the form of like if suppose at a point h if we want to expand, then we can just write this as f of x plus h, that is nothing but like f of x plus h f dash x plus h square by factorial 2 f double dash of x plus all other terms. And if we want to expand suppose f of x minus h, that can be written in the form of f of x minus h f dash x plus h square by factorial 2 f double dash of x minus h cube by factorial 3 f triple dash of x plus the rest of the terms. And whenever we are just adding or subtracting or we are doing some manipulation here, then we are just obtaining this first order approximations or second order approximations for this finite difference form here. So especially if we are just seeing that whenever we are just using this forward difference formulation or backward difference formulation, we are just getting this order of approximation as 1 there. But if you are just using like central difference approximations, then we are just obtaining this order of approximation is 2 here. So what is its overview, or why we are just considering that first order approximation or second order approximation, or what is its benefit, that we will just discuss in this lecture. So if you will just see, so first we are just considering here that it is worth considering exactly what is meant by the order of accuracy of a discretization approximation. Since it is very essential to know whether where we are just using like first order approximation, where we are just using second order approximations, or why we are just using this. So it depends on this discretization formulation there. So if we are just refining the grids, like if we, as we refine the grid for any usual scheme, errors associated with the discretization approximation can be expected to reduce. So especially if you will just see like whenever we are just using this discretization schemes, so suppose we are just starting at suppose I equals to 0, so proceeding with I equals to 1 up to I equals to n here suppose. Then at each of these grid points we are just using this finite difference operators to get this formulation in a difference form here. Like if you will just consider suppose I equals to 1 here, we are just considering for the central difference approximation, we are just considering I equals to 0 and I equals to 2 here. And if we will just refine these grids, this means that this domain, if you are just considering this I equals to 0 to I equals to 1, we can just again discretize this domain into 2 parts there. So then when we want to evaluate this value at the middle point of these 2 grid points like I equals to 0 and I equals to 1, then we can just find that whenever any fitting of polynomial or any fitting of function, if you will just consider for this point, then this error of approximation it will just get reduced. Since directly if you will just consider this function for 2 points, the function will come in this form here. But if you will just consider a middle point in between that one, so again this curve will pass through the middle point. So that is why this difference between this axis, if you will just see here, so that reduces, and this causes the difference for this approximation here also. So this means that as we refine the grid for any useful scheme, errors associated with the discretization approximation can be expected to reduce. And further point is that we reach a grid independent solution, since different grid size if you will just consider, like first if you are just considering h, then h by 2, then h by 4, then h by 8, whenever we are just reducing the size of the grid length thereover, then at a grid point we can just find that there will be no change of solution will come. That is specially called the grid independent solutions. So, when we will just reach for this grid independent solution, this means that for the further grid refinement, we will not find any significant difference in the solution process, and at this stage only the discretization errors are small enough that they can be neglected. So, we have just defined this order of a scheme in terms of leading order error term in the Taylor series expansion. If you will just see for this like a central difference approximation, especially we are just writing this central difference approximation as like f dash x as f of x plus h minus f of x minus h divided by 2h here plus order of certain terms we are just writing here. Whether it is order of h or order of h square, we do not know. So, first if you are just considering if this order is suppose h here, then we can just find that this error of approximation for like particular h, if you will just see, if suppose this is like h here, and sometimes we are just getting this is order of h square suppose. Whenever we are just considering this h square here, this means that h is a very small quantity, and whenever we are just considering this term as in square sense, this term will have a very less effect on the solution process. But if you will just consider only h here, then since it has a small value, so that is why it may be contribute something in the solution process that may create the problem. So, that is why this should therefore determine at what rate the error reduces as the grid is refined here. This means that whenever we are just doing this grid refinement, we have to consider that how much small scales we can just go, or how much small length we can just consider for a special grid size, that these errors will not reduce after certain stage that we will just consider here over. Suppose for a first order scheme, if the grid spacing is halved, then the error is halved. So, if you will just see. For a second order scheme, if the error would reduce, then it will be like order of h square. So, that is why you can just consider as like h square by 4 there. So, this means that error will be reduced by like factor of 4 there itself. So, that is why this is the benefit we can just get if you will just reduce this like grid length, or whenever we are just going for this higher order like neglection of these remainder terms. So, note that you should have to keep in mind that this does not mean a second order solution on particular grid will always be more accurate than a first order one, although this will useful or this will be usually be the case for a sufficiently fine grid here. If you will just see, so sometimes we are just considering like first order approximations or accuracy, or sometimes we are just considering like second order accuracy for a particular grid. Since at that point only we are just considering like either the 2 points, or we are just extending to like a forward marching or a backward marching there. So, this does not mean any like a particular grid it will be affect that the more accuracy of the solution there. So, it does that, however, imply that as we refine the grid, the error in the higher order scheme goes down more rapidly. So, we expect the higher order scheme to reach a grid independent solution on a coarser grid than would be required for a lower order scheme. Since whenever we are just going for like finer grid solution process, then especially the error will be fast reduced there. But if you will just go for like larger grid lengths there, then this error will not be converged in a smooth form there. This means it may be take some time that it can just reach to that level. So, it is worth when noting that the behavior described above for a particular scheme can only be expected on a reasonable fine grid. So, from this we can just observe that whenever we are just going for this fine grid, so then we are just finding that it can just give us this best approximated solutions. So, then if in a numerical sense, if you will just go for this first order approximation here, that in the Taylor series expansion, for example, in the first order backward difference scheme, we are just considering like f dash of xi. Since we are just considering here the series as in the form of like f of x plus h, that is like f of x plus h f dash x plus h square by factorial 2 f double dash x. So, likewise, And if we are just considering like f of x minus h here, this can be written in the form of f of x minus h f dash x plus h square by factorial 2 f double dash of x minus rest of the terms here. And if we want to separate suppose f dash x for this backward difference scheme here, then especially we are just writing that as f of x minus h minus f of x by h, that is nothing but here as minus f dash x plus all other terms are there. And if you will just change the sign at both the sides, then we can just obtain the solution as in the form of like f dash x, this equals to f of x minus f of x minus h divided by h plus rest of the terms thereover. And especially for this case, if we are just considering this grid sizes are like, if suppose the starting point is, if we are just considering here, that is in the form of like starting is from this to there, and then we are just starting x0, x1, x2, x3 up to xn is the last point here, then especially we can just say that this difference can be defined at a particular point. Or we can just say that if xi is the point where I is varying from like 1, 2, 3, so likewise, or we can just consider this is 0, 1, 2, 3 likewise here, then we can just say that we can just f of xi can be defined at all the points here, that means we can just write f of x0, f of x1, f of x2 at each of the points there. Then at a particular point, if we want to find this finite difference approximation in a backward sense, then we can just write this as like f dash of x we have just defined as f of x minus f of x minus h divided by h plus rest of the terms we have just defined. And at that point, if you will just write here like f dash of xi here, then this is xi, then this is xi minus h here, then all of the order terms that will also involving this term h into multiplication of rest of the terms there. Since if you will just divide here h, so then the first order h can be come into the picture. So whenever we are just have a like second order differentiation here, so h square by h, that will just give the h term thereover. So that's why if we will just go xi minus h means we are just going back to one of these points there. Since the space size is defined as h here, so that's why if you will just consider like xi is the point, suppose x3 here, then if xi minus h means we can just go to the back of the one point, that we can just say as the x2 here. So if you want to evaluate suppose f dash of x3, then we can just write this one as like f of x3 minus f of x2 divided by your space length, that is nothing but h here. And especially in the particular slide, we have just considered this distance as the, since we are just moving in the x direction, we can just say that space length is defined as del x here, that is h equals to del x we have just considered for this expansion here. So that's why we are just writing this f dash of xi is nothing but f of xi minus f of xi minus 1 divided by del x plus h by 2 factorial, especially we are just writing, that is nothing but del x by 2 factorial here, f double dash of xi and minus of del x whole square by 3 factorial f triple dash of xi plus order of delta x q terms. Since after this term, so this term will be the coefficient of this like f fourth of derivative thereover. So if the first term in the truncation error is the leading term here, if you will just consider here, so this term is associated with this coefficient, that is del x here over. And if we want to find suppose for this like a coarser grades, if you will just say, or finer grades, then we can just find that del x by 2 is into your absolute of f double dash of xi here. This is always larger than this del x whole square by factorial 3 f triple dash of xi. Since whenever any polynomial differentiation we are just taking, then this polynomial differentiation always reducing to some powers also there. Suppose if you will just consider like f of x equals to x to the power n, then f dash of x we are just writing nx to the power n minus 1 here. This means that it is just reduces to the power by 1 also there. And if you will just see here, this del x square, since it is a small term we are just considering here, or del x is a small value, so its square of approximation means always it is less than del x also here. And if you just consider this del x size, especially in the final step here, so then we can just find del x should be always less than 3 into f double dash of xi by f triple dash of xi here. If we will just go for like this order of approximation, always we can just find that whenever we are just going for like second order approximation or third order approximation. In the last lecture we have just discussed that whenever we are just going like second order approximation, you can just find that this third order term, whatever it will be associated with this derivative term here. So that will be always less than this like second order term thereover. So this means that whenever we will just go for this finer grid or very small grid sizes, then we can just find that there will be no change of solution we can just find. This means that the solution will be always equal, or whenever we will just consider this in the last neglected term is the larger compared to the remaining term that we are just neglecting, that will also be a sufficient condition for this order of approximation there. So then we will just go for this polynomial fitting, especially whenever we are just defining this finite difference approximation. So especially we are just applying this approximation always in the differential sense or in the integral sense there. So if we are just using this differential sense, then we will always get a polynomial in the final stage. So if we are just getting this polynomial, how we can just fit this polynomial with this function or with this grid points, that we will just discuss here. So if you will just see this above expressions, whatever we have just discussed, that is the finite difference formulations based on this Taylor series expansion, that are specially involves these derivative terms, which could be derived by fitting a polynomial to the function f through these grid points, that is defined in the form of xi here, and surrounding points, and then differentiating this polynomial to obtain its gradient. And the forward and backward difference schemes arise from fitting a first order polynomial through the points like xi, xi plus 1, xi minus 1 and xi. Since if you will just see this like forward difference formula, especially we are just writing that at the particular point, suppose if you will just see f dash of xi, it can be written in the form of like f of xi plus 1 minus f of xi divided by h there. And similarly we are just defining this backward difference scheme, if you will just see here. So f dash of xi, it can be written in the form of f of xi minus f of xi minus 1 divided by h there itself also. So that's why, so this function whatever it is associated with the grid points, so if we can just fit it with a polynomial, it is very easy to get this differential formulation there itself also. So for the central difference, it can be obtained by fitting a quadratic curve through these points like xi minus 1, xi and xi plus 1, especially if you will just see here. So 3 points we can just consider for this central difference approximation, since we are just going one forward march and one backward march. So backward march means we are just considering towards the point xi minus 1, and forward march means we are just considering xi plus 1 here. So if we are just combinedly just fitting with a curve here with these 3 points, especially since we are just writing this finite difference operator, combining these 3 points in a functional form with certain operators there, especially that is not just generating a polynomial there itself. So then this will just generate, since the 3 points are involving for this function here, so that will just generate a polynomial of degree 2 there. So that's why we are just saying here fitting a quadratic curve through these points xi minus 1, xi and xi plus 1 here. Then if you will just go for a linear fit, that is for like 2 points formulation here, either we can just consider xi, xi plus 1 or xi, xi minus 1 here. So for this polynomial, if you will just see here, we are just considering this point, suppose like xi and xi plus 1 here. And if you will just generate a polynomial function then this polynomial can be written in the form of like x minus xi plus 1, especially this one we can just say as a Lagrangian polynomial here, that is nothing but like L0x. If we have like 2 points here x0 and x1, then especially we are just writing this as x minus x1 divided by x0 minus x1, and L1x, if you will just write, this can be written in the form of like x minus x0 by x1 minus x0, and the total polynomial especially it is just written in the form of like L0x f of x0 plus L1x f of x1 here. And if you will just formulate for these points like xi and xi plus 1, especially we can just write this as Li of x as x minus xi plus 1 by xi minus xi plus 1, and Li plus 1 of x, this can be written in the form of like x minus xi divided by xi plus 1 minus xi here. So, obviously, if the complete polynomial can be written, so this complete polynomial it can be represented in the form of like x minus xi plus 1 divided by xi minus xi plus 1 into f of xi here, plus x minus xi f of xi plus 1 by f of xi plus 1 minus xi here. And if you will just see that whenever we are just considering these differences here, that is nothing but the del x size we are just considering here, or space length as h especially we are just considering here. So, that is why we can just write xi minus xi plus 1 here as minus h or minus del x here. So, this complete formulation we can just write as x minus xi plus 1 by minus of del x into f of xi here, plus x minus xi f of xi plus 1 divided by del x here. And the derivative of this function, if we directly we will just take this difference of this function here. So, this means that we will have an associated term x here, we will have an associated term x here, we can just differentiate directly for this function here. So, f dash of x, especially if you will just write here, so first del x is a constant here, we can just take it out, then it can be written in the form of like f of xi divided by like minus of del x, and this term especially if it can be written, it can be written as fi plus 1 by del x here. So, the complete differentiation if you just write here, that is f dash x, it can be written in the form of like minus of fi by del x plus fi plus 1 by del x here, which is just written in this form here, that is fi plus 1 minus fi by del x. And if you will just go for this quadratic fit of this polynomial, the central difference scheme if you will just see, it can involve 3 points here as we have known, that is xi minus 1, xi and xi plus 1 here. So, 3 points in a combined form if you will just consider here, that can just generate a polynomial of degree 2. So, especially in a Lagrangian form if you will just write this polynomial as Li minus 1 of x f of xi minus 1 plus Li of x f of xi plus Li plus 1 x f of xi plus 1 here. And since it involves 3 points, especially if you will just see with each of distances del x here, so you can just write these points as in the form of xi minus 1, xi plus 1, and the functional values associated with these points are in the form of f of xi minus 1, f of xi and f of xi plus 1, which can be written as like Li minus 1 of x here as x minus xi x minus xi plus 1 divided by xi minus 1 minus xi xi minus 1 minus xi plus 1. Similarly, you can just write this Li of x as x minus xi minus 1 x minus xi plus 1 divided by xi minus xi minus 1 xi minus xi plus 1 here. Similarly, we can just write Li plus 1 of x as x minus xi minus 1 x minus xi by xi plus 1 minus xi minus 1 into xi plus 1 minus xi here. So, if you will just combine this 3 points in a polynomial form here, that we can just write this one as like, if you will just see here, x minus xi, x minus xi plus 1 divided by xi minus 1 minus xi, xi minus 1 minus xi plus 1 into your f of xi minus 1 plus x minus xi minus 1 x minus xi plus 1 divided by xi minus xi minus 1 xi minus xi plus 1 into f of xi plus x minus xi minus 1 x minus xi divided by xi plus 1 minus xi minus 1 into xi plus 1 minus xi into f of xi plus 1. So, if you will just see here, so this is a complete formulation of this polynomial there. And on a uniform grid, since we are just considering this 3 grid points are placed at equal distances, we are just considering this as del x here, this as del x here. So, that is why we can just write xi plus 1 minus xi, this equals to xi minus xi minus 1, this is nothing but del x here. And if you just take this combination of these two distances like xi plus 1 minus xi minus 1, this can be written as 2 del x here. So, that is why if you just write in a complete form here xi minus 1 minus xi, it can be given you like minus del x here, and it can be xi minus 1 minus xi plus 1 here. So, that will just give you like minus 2 delta x here. So, combinedly it will just give you 2 delta x square here. Similarly, if you will just find here, this will just give you minus delta x square, since xi minus 1 this is delta x, but xi minus xi plus 1 this will just give you minus delta x here. So, that is why this is just giving you minus delta x whole square here. So, if you will just take the derivative for this function here, then this derivative f dash of x can be written in the form of like x minus xi plus x minus xi plus 1 into f of xi minus 1 by 2 del x whole square plus x minus xi minus 1 plus x minus xi plus 1 divided by minus of delta x whole square into f of xi plus x minus xi plus x minus xi minus 1 into f of xi plus 1 by 2 del x whole square. And then we can just write this f dash of xi as in the form of, if you will just see here, so x 2x it is there, and if you will just see here, this is nothing but minus of xi minus xi plus 1 here into fi of minus 1 here. And if you will just see, this is nothing but 2 del x square here, and this is if you will just see all the terms, it can just cancel it out here, since minus sign it is, if it is just present it over there. So, combinedly if you will just take all these terms, so then we can just write this f dash of xi, that as like if you will just replace here xi minus xi, that will just give you 0 here. So, xi minus xi plus 1. So, especially this will just give you here minus del x. Then if you will just see xi minus 1, this will just give you delta x here, and xi minus xi plus 1, this will just give you minus delta x. So, that is why this is just cancelling each other, this is just giving you 0 here. And if you will just see here xi minus xi, this is just giving 0, xi minus 1, this is just giving you delta x. So, that is why this is delta x here into fi plus 1. So, finally, we are just getting this f dash of xi, this is equals to s f I plus 1 minus fi minus 1 divided by 2 delta x. So, if you will just go for like a second order differentiation here, so that the previous differentiation, once more differentiation if you will just consider here, that is f double dash of x for this equation here, then we can just find that since 2x it is just present it over there. So, that we can just write as 2 by 2, it can just cancel it out. So, that is why it can be written in the form of fi minus 1 by del x square. And if you will just see this like this term also here, that is nothing but 2x here. So, that is why it can be written also like 2 into fi this will also be written as a 2 into fi plus 1. So, all these terms, this differentiation if you will just consider, that can be written in the form of like fi minus 1 minus 2 fi plus fi plus 1 by del x whole square. And this expression if you will just see, this is identical to the formula that whatever we have just obtained in Taylor series expansion also. Thank you for listening this lecture.